All right, so welcome back. Today in this video, we are going to be continuing our Civil FE exam review by going through a topic that is covered in structural engineering. And that topic is specifically load combinations, and load paths. So if you have not checked out some of the other videos in structural engineering, like column analysis, deflection of statically determinate beams, or any of these other videos, definitely check them out. I have gone through and talked about some conceptual things that you'll need to know for the exam. All right, so let's look at these practice problems. So number one says, consider a reinforced concrete beam subjected to a dead load of 20 kilonewtons per meter and a live load 30 kilonewtons per meter. Calculate the ultimate factored load using the load combination 1.2D plus 1.6L. Okay. So start out by writing out what we're given. We are given dead load. We're also given live load. And we are given the load combo that we need to use. Okay. So we're trying to find the ultimate load combination. I can tell from my answer that it needs to be in kilonewtons per meter. So what formulas would I need? Well, if you're not familiar with load combinations, what are they? Let's look up load combinations. All right. All right. So load combinations ultimately is saying, hey, we're going to put some factors alongside or we're going to put factors on our different loads, right? So we're going to account for things like rain, R, snow, S, wind, dead loads, earthquake loads, live loads. What do we mean by this, right? So you have this in this particular situation, a concrete beam, right? And I'll just draw a beam. Got this beam, right? And we got it raining, the rain load. This is just random, right? But I'm just trying to explain that, for this particular beam, right, you're going to have a rain load. And so in some of these combinations here, it accounts for these different type of things, right? You can, in this particular formula, it would be 1.2. So you got some dead load. And dead load is the weight, could be the weight of the beam. It could be the asphalt that's coming across, maybe a bridge, just stuff that's going to be there that's not going anywhere. That's there pretty much until you remove the whole structure. All right, then you got live load, so you could have people walking. So say you got some people that want to walk in the rain, all right? Well, now they weigh something, right? So that's some live load happening. You got earthquakes that could happen, right? Or you got snow that could take place, or you got wind, that can blow at the beam. So all different types of things that structures have to go through. Would not want their problems, right? But for this particular example, they are just asking us to use the load combination of 1.2D plus 1.6L. So 1.2D plus 1.6L. All right. And if we do that, what is the ultimate factor load that we will get, right? So what is my dead load? Yep. So my dead load is going to be equal to 20 kilonewtons per meter. My live load is equal to 30 kilonewtons per meter. And so I'll do 1.2 times 20 kilonewtons per meter plus 1.6 times 30 kilonewtons per meter. And that's going to give me my ultimate load, right? Which when I plug this in, I get 72 kilonewtons per meter. And so I get C. Number 2. What is a good example of dead load in a structural system? Okay. So we're given dead load, right? Or that we need to find dead load. Or that's the highlight, what we're trying to do. So dead load, we're also given that we're in a structural system and we're trying to find what's a good example. All right. Okay. Got all these different things. So would wind force be an example of dead load? Well, dead means it's there and it's there for pretty much ever. So is wind always there? No. Is the same amount of wind always there? No. Would, and I also, and dead load also means that it's normally not moving. So that's another key thing. Okay, so would occupant furniture be one? Well, if the furniture sits there, right, doesn't go anywhere, they're not moving it, then yes. Right. Earthquake vibrations. If you're having earthquake vibrations all the time, that is would not want to be there, or would not want to be that structure. And then live concert audience, right? And that's no as well. All right, that's they come in, you have that big amount of load, and then hours later they leave. They're drunk, partying, had a good time, but now they're high, maybe. Now they're gone. All right, so no live concert. Your answer would be B. All right, so number 3 says, in load combination calculations, what distinguishes the allowable stress design approach from the load and resistance factor design method? Okay. So, what information are we given? We're given the ASD method, right? The allowable stress design, right? And we're given the LRFD method, or the load and resistance factor design method. Okay, so we're trying to find what distinguishes. I spelled that wrong. But basically, what's the difference? What difference? What's the difference? All right. So, are there any formulas that we need? Not really. We're gonna just go into this. I mean, we have the comparisons up as well. So if we need to use a formula, we can kind of look and see, right? So the ASD uses a single fixed safety factor for all load combinations. Do they? No, they use some different ones. I don't think that's not even true. LFRD incorporates different load factors for each load type and combination. Yeah, so they are incorporating different load factors for each load type. So 1.4, 1.2 D, 1.2 D, 1.6, and 0.5. Yeah, so they have these different factors for each type. And so does ASD. But they don't have the same load combinations, right? ASD solely relies on ultimate strength considerations. They both rely on. So no. LFRD employs a constant safety factor throughout the design process. No. The answer is going to be B. So really the main difference is they have different load combination factors, right? So this one has D for that first one, which represents dead load, and then the next one is dead load plus live load. And then for the LRFD method, you have 1.4 D, so that's a factor, right? A load combination factor, right? Then you go to 1.2 D plus 1.6 live plus 0.5, and you even incorporate these different variables, right? So LRFD definitely incorporates different load factors for each of the combinations, whereas in ASD they don't put load factors in front of some of their combinations, right? All right, so this concludes the loads, load combinations, and load paths. Next video, we're going to be looking at some actual design. So this is pretty in-depth, so you definitely don't want to miss the design of steel or concrete component. So I will see you in the next video.